beta hat is given by x transposed x inverted times x transposed y. So the question is now, what is the expectation of our point estimator? So how can we show that? So what's the expectation of our point estimator? Well, we can just put in what it is, namely what we have here, x transposed x inverted times x transposed y. And we know what is y, because y is obviously given by x times beta plus epsilon, which is our residual vector. So what we have to do now is we just plug in what it is. So what we have then is the expectation of x transposed x inverted x transposed times x times beta plus epsilon. Yeah. Now we have just plugged in for epsilon what it is, this equation, our standard linear regression model. Now we just need to multiply out what it is. So with the first term, with the first term and the parentheses, and then what is before the parentheses with the second guy here. So maybe we can need a little bit more space now here. So first we have obviously x prime x inverted times x prime x inverted, and prime and transposed is obviously a synonym. Whenever I say prime, I mean transposed, and whenever I mean transposed, I mean x prime. It means the same thing. So times x, times x times beta plus, again, what is here before. Now we take it, we have to multiply it with the second part of the what is in parentheses, which is epsilon. So x prime x inverted times x prime plus times epsilon. Okay. So what we see now here is the same thing that we have already encountered. So what we have here is we multiply a matrix product with itself inverted. So what we have here is nothing else than the identity matrix times beta. And we know the identity matrix times beta is beta. Yeah? So what we have here in the first term is just beta. And that's the number, and this is just numbers. Beta contains just numbers, namely the true parameters, right? And the second term, and the expectation of a number is just the number. So the expectation of beta is beta. So we don't need the expectation operator here anymore. So what remains? We have on the second term, what is here in the expectation operator, we can move the expectation operator, because it's a linear operator, we can put it here. Yeah? So what remains is, so expectation of beta hat is beta, obviously, because the expectation of beta is beta, because beta contains just numbers. So plus the expectation, now we move the expectation operator in the parentheses, expectation from this guy here, x prime x inverted times x prime epsilon. So now the question arises, what is random here? Yeah? So according to our OLS assumptions, x is predetermined. That's not random. The only thing that is random is our epsilon. Because epsilon is random, we can move the expectation operator one step further. We can move it here. So what remains then, let's do that. So what remains then is the x prime x inverted times x prime times the expectation of epsilon, right? And we know, according to our assumptions, the expectation of our residual vector, of our errors, is 0. Yeah? According to our assumptions. So this guy here is equal to 0, and because this guy here is equal to 0, everything here becomes equal to 0. Yeah? That means the expectation of our OLS estimator is beta. The expectation of beta hat is beta, which means that our point estimator is unbiased. Yeah? It gives us on expectation the correct point estimates. Yeah? Of course with a small error marginal, because of course we have to derive the distribution as well, but the expectation of our point estimator is beta, so it's unbiased, which is a very important property. And you can Google, if you have time, you can Google it. The so-called Gauss-Markov theorem shows that the OLS estimator is blue. Blue means best linear unbiased estimator, which is an important property. So, and what we also see here from this equation, because we will need this later on when we derive the covariance matrix of our point estimator. So what we see from this equation is that we can, if we move this on the other hand and we take away the expectation operator, so what remains is basically like an intermediate step of this analysis, is that beta hat minus beta beta hat minus beta is equal with x transposed x inverted times x transposed epsilon. Yeah, so this is an intermediate step from this analysis here. Yeah, if we move this on the left hand side and we take away the expectation, we neglect from the expectation operators, what comes out is beta hat minus beta is equal to x transpose x inverted x transposed times epsilon. Yeah, that's an intermediate step from our analysis. This is important to bear in mind because we will need it later on. So, and now you may ask, okay, we have assumed that our regressive matrix is not random. The only random component is our epsilon here. But what if x is also random? Because obviously the stock market is obviously not cannot be controlled like in an experiment. So the stock market or any other risk factor that we use in asset pricing research and finance is obviously random, right? So, but that doesn't matter for our current context. Yeah. So what one can show is the only thing that we have to do is we have to take the conditional expectation. Yeah, you might remember that. So if we take the expectation from beta hat given our regressor matrix, if we now assume the regressor matrix is also random, what we can show is that it's also beta. So it doesn't change. So the derivation is pretty much the same thing. So the only thing that is important in showing this is that the error term is uncorrelated with the regressor matrix. Yeah? So whenever the regressor matrix is uncorrelated with the residuals, we can do this operation. Yeah? We can move in the expectation operator. Instead of having it here, we can move it further. Yeah? Here. So if we take let's say in the case of a random regressors, we need a little bit space here. Let's take away something here. So if x and epsilon, if they are uncorrelated, what we can do is we can move the expectation operator here in. So expectation of x transposed x inverted times x transposed times the expectation from epsilon. Yeah, and we can, and once again, we can only do that if epsilon and x are uncorrelated. So, and what comes out is the same thing, because if our epsilon are 0, even if this guy here is not 0, the whole term becomes 0, because whatever you multiply with 0 is 0, okay? So it doesn't change the end result, okay? And I told you earlier that that's basically not a problem in our research context, because it would be a problem if we have lagged dependent variables. Yeah? If our X matrix would contain some lagged variables from the left hand side, so some lagged Y variables here. If we had lagged Y variables in our regressor matrix, then obviously this is a problem and we have to operate with other concepts. Yeah? But in certain cases we can show that OLS is at least consistent. Yeah? But in our case, yeah, we don't have to bother with that. So we can simply assume, yeah, that these guys here are uncorrelated, and so we have the same result. So the conditional expectation on x is beta, like in the previous case. Yeah? So, and the same is true for all the derivations that follow. Yeah, for simplicity, we assume that our x is predetermined. Yeah, but you can have in mind that even if it's not, even if it's random, but as long as it's uncorrelated, so the same formulas and the same concepts hold as well. Okay. Just for that you have a little bit more background knowledge here. Yeah, but we keep it simple. So we assume still that x is predetermined and so on, so we can operate with this framework, and we know that that the expectation of our point estimator is unbiased. Yeah? So it's a very, very important result. So let's take this away now. Another important result is that in order to show that our point estimator is unbiased, it doesn't require the assumption of a normally distributed random term, right? the only assumption was that it is 0, that the expectation is 0. It's not either required that the error term has the same variance across time. Yeah? So irrespective if we have volatility clustering in the data, or if the data is not normally distributed, our point estimator is unbiased as long as the error term is on expectation 0, which is also an important result. So now the next question is, okay, if we want to make statistical inference, we are interested in the corresponding t-statistic. We want to know if our point estimator are statistically significant or not. And since we assumed in our OLS assumption that the error term is normally distributed, what follows is that our point estimator, our beta vector, is normally distributed as well. Okay, which is also an important to know. So what does that mean? So it means that we have this kind of probability function for every parameter that we have. For our alpha, for instance, so if this is our estimated alpha, it follows a certain distribution. Our point estimator might give us a value here. This might be the corresponding value, and then we want to know if our point estimator is statistically different from 0 or not, right? So what we have to do is we have to figure out the variance of our alpha in order to estimate the probability distribution. And once we have that, we can calculate the t-statistic of our